Okay? But I want to show how we can use Pascal's triangle to find the patterns for the next two special product forms. Okay, so Pascal's triangle is created by just increasing or for each consecutive row, and we start with row 0. The top row is row 0. What you're going to do is you're just going to add ones to the outside and then fill in your terms in between those with the diagonal sum of the two terms above it. And so what's the diagonal sum of the two terms above this space right here? 1 plus 1 or 2. So if we look at the next row, this sum of these diagonals is 3, and these are 3. And if we go one more, we get 1 and 1 on the outside. What would be the pattern of our numbers across here? 4, 6, 4, and 1. All right, now this can continue indefinitely. Keep going down the rows, but I want to talk about how Pascal's triangle relates to binomial powers. Okay, which are the binomial square and the binomial cubes are what we have left to look at. All right, if we took a binomial, a plus b, to the power of whatever our row is determining. Okay, what's anything to the 0 power? 1. Okay, so we see that is shown right here, 1. All right, what if we go to row 2? So if row 1. We started with row 0. Okay, so if we go to row 1, we get our binomial power to the first. Okay, so what is anything taken to the power of 1? Itself, right? So this is just a plus b. Now, if you notice here, the row in Pascal's triangle is always going to relate to the coefficients of the terms in our binomial expansion. So here, if we take our first term a and put a to whatever power the row is on the first term, and then reduce the a's for each consecutive term. So this is a to the first, so as we move from left to right, our next term will be a to the 0. Do I need to write a to the 0? No. And we'll do the same thing with the second term, but move from right to left. So we'll start with the second term on the far right to the power of whatever the row is. So again, each of these is a power of 1. And then as we move to the left here, we're going to decrease the power of b by 1. So the first term would be b to the 0. Again, don't need to write it. And what you see right here is you get your pattern a plus b. And so let's take a look at row 2, which coincides with a binomial square. Okay, so if you look at here, we have our coefficient pattern of 1, 2, 1. Okay? And again, if we start with our first term to the power of whatever the row number is, so a squared, and then each consecutive term, as we move to the right, you reduce the power by 1. A to the first, a to the 0, so don't even write it. Take our b, our second term, to the highest power, the row 2, and then as you move to the left, power of 1, power of 0. And what you see right here is we get our expansion pattern to be 1a squared plus twice ab plus b squared. And that's exactly what we got when we FOILed this out in the previous slide. Okay, so what do you think row 3 will yield? If you take a binomial cube, okay, you can see our expansion pattern for the coefficients is 1, 3, 3, 1. So we take a to what power to start with? We're in row 3, so it's cubed, and then squared, and then to the first, and then to the 0. And for b's, we're doing the same thing, but working from right to left. Start with the highest power, 3, 2, 1, 0. And what we find right here is our expansion pattern of a cubed plus 3a squared b plus 3ab squared plus b cubed. And if we were to extend this, even if we wanted to, and you don't have to, you only need to do these two. But if we were to expand a binomial to a power of 4, it would be a to the 4th cubed squared first nothing B 4, 3, 2, 1, nothing. And so this would be our expansion pattern for row 4, or for a binomial to the power of 4 if we wanted to go that far. And you can continue again infinitely down for these.